In this video, I will show you an example of solving a non-homogeneous second-order differential equation with the method of variation of parameters. Differential equation is y double prime minus 4y prime plus 4y equals to e to the 2x over x squared. The general solution of a non-homogeneous differential equation, if we suppose y to be the general solution, is the sum of complementary and the particular solution. For finding the complementary solution, first we have to solve the homogeneous corresponding equation, which is this equation, y double prime plus minus 4y prime plus 4y equals 0. We have to solve this homogeneous differential equation. We say this differential equation is homogeneous because we set it equal 0. To find the complementary solution. After we find the complementary solution, we can find the particular solution. For finding the complementary solution, first we have to write the characteristic equation r to the 2 minus 4r plus 4 equals 0. If you don't know how to solve the homogeneous second order or higher order differential equation, watch my videos about solving homogeneous differential equations. Now we have to find r from this characteristic equation. We can factor it as r minus 2 times r minus 2 equals 0. Or you can use quadratic formula for finding r. From this, r equals 2. If we set this equals 0, r equals 2. If we set the other bracket equals 0, r again is 2. So 2 is a repeated root for this quadratic equation. And it is very important. We know that when we have repeated roots, say the repeated root is r, the solution of the homogeneous differential equation is c sub 1 e to the rx plus c2x e to the rx. We know this formula. If we use this formula, the complementary solution is c sub 1 e to the 2x plus c2x e to the 2x. Now that we have the complementary solution, we can find the particular solution from this formula. The particular solution is always negative y1 integral of y to f of x over Wronskian of y1 and y2 dx plus y2 integral of y1 f of x over Wronskian of y1 and y2 dx. For solving and finding the particular solution of a second order non-homogeneous differential equation, we can use this formula. This formula is for the method of variation of parameters. But what is y1, y2, f of x, and Wronskian of y1 and y2? y1 and y2 are the two functions that we found here. y1 is e to the 2x in this example, and y2 is the other function that we found in the complementary solution. So y1 is e to the 2x and y2 is x e to the 2x. F of x is the function in the right side of the equation. So e to the 2x over x2 is f of x. But what is Wronskian of the two functions y1 and y2? What is Wronskian in general means? Wronskian of two functions, Wronskian of y1 and y2 in general, is a determinant like this, which the first row is y1 and y2, the two functions that here we have, and second row of this is derivative of y1 and y2. So we have to take the derivative of these two functions and put them in the second row. Then by calculating this determinant, we can find the Wronskian. But if you don't know how to calculate this determinant, this is how we find a determinant like this: y1 times y prime 2 minus y2 times y prime 1. For finding the particular solution, let us start with finding the Wronskian. And one thing that I should mention here is that we can use this formula for solving second order non-homogeneous differential equations if the coefficient of y double prime is 1, like here. And if the coefficient of y double prime is not equal to 1, first make it equal to 1. Divide both sides of the equation by that coefficient to make the coefficient 1. Don't forget, it is very important. Otherwise, your answer is not correct. So, we want to find the Wronskian. Wronskian of the two functions e to the 2x and x e to the 2x is, put the two functions here, e to the 2x and x e to the 2x. Derivative of e to the 2x is e to the 2x times 2. We have to take the derivative of the exponent based on chain rule, it's 2. So derivative of e to the 2x is 2e to the 2x. But for finding the derivative of this, we have to use the product rule, x times e to the 2x. Derivative of x is 1 times e to the 2x plus, write the first function, which is x, multiply by derivative of e to the 2x. But we see here that derivative of e to the 2x is 2e to the 2x. So 2e to the 2x. And this equals to, multiply this by this, e to the 2x times e to the 2x plus 2x e to the 2x minus, multiply these two, x e to the 2x times by 2e to the 2x. Now if we multiply this e to the 2x in the bracket, e to the 2x times e to the 2x is e to the 4x. And if we multiply this e to the 2x in this bracket, we have 2x e to the 2x e to the 2x. And we have exactly negative of that term here. So they cancel each other and only this remains. So the Wronskian is e to the 4x. Now that we have the Wronskian, let's calculate these two integral. Integral of y2. What is y2? Is this expression, x e to the 2x times by f of x. F of x is this expression that here we have, e to the 2x over x, to all of this over the Wronskian, e to the 4x dx. If we simplify this, note that e to the 2x and e to the 2x multiply by each other, and we have e to the 4x, which if we cancel with this e to the 4x in denominator, only we have x over x2, and x over x2 is 1 over x. And integral of 1 over x is ln of x, or ln of absolute of x. And it is very important, do not put the constant c here when you are finding these integrals in this formula. For the other integral, we have integral of y1 is e to the 2x times by f of x e to the 2x over x2 all over the Wronskian e to the 4x dx. E to the 2x times e to the 2x is e to the 4x, which cancels with this e to the 4x in denominator. Finally, this remains in this integral, 1 over x to dx. We can write it as x to the negative 2, and integral of x to the negative 2 is x to the negative 1 over negative 1, which we can write it as negative 1 over x. And this is the second integral. Now that we calculated the integrals, we can find the particular solution. The particular solution equals to negative y1, negative e to the 2x, times by the integral. The first integral is ln of x, so times by ln of x, or ln of absolute of x, plus y2. y2 is negative 1 over x, times by, oh sorry, this is the integral, not y2. y2 is this expression, x e to the 2x times by negative 1 over x. This integral is negative 1 over x, y2 times negative 1 over x. And note that we can cancel this x with this x here. So we can write the particular solution in this form, negative e to the 2x ln of x plus, or actually minus, here we have a minus, minus e to the 2x. But if you pay attention to the complementary solution and the particular solution, you can see that in the particular solution we have e to the 2x, and in the complementary solution also we had e to the 2x. So we have a term in the particular solution which is exactly duplicated in the complementary solution. So what you can do here is that you can ignore and eliminate this from the particular solution. So you can say that the particular solution is only this part. But it's up to you, you can leave it here, but if you want, you can say the particular solution is only negative e to the 2x ln of absolute of x. And if we add the particular solution to the complementary solution, we can write the general solution. The general solution is the sum of complementary solution and the particular solution. I hope by watching this video you have learned a bit about solving second order non-homogeneous differential equations with the method of variation of parameters. If you like this video, please subscribe in my channel and see you in the next videos.